Okay, so hi everyone, and thank you for coming. My name is Danny, and I came here from Tel Aviv. This is actually my first time here at the NodeConf Budapest. And I'm doing security research at Snyk, searching for vulnerabilities in open source code and basically building our vulnerability database. Snyk is a dev tooling company. We are based in Tel Aviv and in London. And we're building tools for developers to help them consume open source code securely. And we have a lot of office dogs. In my past, I've been doing development in different startups and later worked as a CTO in a security consulting company and doing security research and crypto analysis. I also really enjoy playing capture the flag games with my team at Astan, and these are security competitions where different teams try to compete one against the other by hacking the systems of the other teams and defending their own from being hacked. And 3 weeks ago, my team had the honor to win the CCC Capture the Flag, and it's an event held in Hamburg, Germany. So at Snyk, we're big fans of Node and NPM, and obviously we're not alone. NPM usage has exploded. There are more than 380,000 packages on NPM registry, and with 6 billion downloads per month, and 65,000 publishers. So these are staggering numbers, and they keep on growing in an insane pace. So clearly, JavaScript has won, and definitely in the speed of growth and the reach of the community. So it leads to a situation where a typical Node application has somewhere between hundreds up to thousands of dependencies, and Daniel talked about it. So those are, some of them are direct dependencies. These we see in our package JSON files, right? But the majority of them are actually indirect. We just pull them into our application and making them our own code. So it leads to a situation where this is our own code, the code we wrote, and this is our app. And the orange part here are the NPM dependencies, the code we pulled in and making it our own. So this is actually a positive slide because we can create all this value by writing this little purple circle and just focusing on the core. But with that comes security risks, of course, and first question is like, do we even know what dependencies we pull in, what dependencies we end up with? Do we know if the developers had any security expertise or whether the code went through any security testing? Whether it's a well-maintained code and the bugs or security issues that get reported to the maintainers are addressed in a timely manner. And finally, do we know if every single dependency has any known security vulnerability? So we tested in October last year, we tested all the NPM packages with Snyk, and we found that 14% of them carry known security vulnerability, either directly in its own code or in one of their dependencies. And roughly 4 out of 5 Snyk users find vulnerabilities in their own apps when testing for the first time. And so now I'll be going to show you a vulnerable application, a sample vulnerable application, and walk through a process of finding these issues and fixing them with Snyk. And also we'll be looking in depth into 3 different vulnerabilities in popular NPM packages. So this would be a good learning opportunity to see a real-world software written by experienced developers that had a security issue that later got fixed, and hopefully we can learn something from that. So yeah, I'll post the slides later. These are the URLs and the application, this demo application is available on our GitHub. So I'll just switch it here. So this is Goof. This is a demo MVC to-do app. It's pretty simple. We can add to-do items. Maybe zoom in a little. I hope the Wi-Fi holds. We can emphasize things with, you can say, by here we can use Markdown here. So it's pretty basic. We have some awesome about page here. And if we look at the package.json file of this app, it has 20 dependencies. Not too many, pretty standard. So the first step I'll do is to go to Sneak and test my GitHub repositories for the known vulnerabilities in the NPM packages. So I have plenty here, but what we are interested in is goof. Let's wait for a second here until the test completes. So we see we have some vulnerabilities. Again, this is a demo application. It has 14 vulnerabilities here. And if we go to see the details of the report, we see that there are the list of the vulnerabilities sorted by severity. So we see the number, the name of the package, the vulnerable version, how it was introduced into our application, and some description about the vulnerability. You can actually get more info here. So I'll take the first example I will use is the ST. Anyone here familiar with the package ST? No? Okay, some hands. So ST is an express middleware used to serve static files. Basically, these are the files that the JavaScript, the CSS, and the images that our application serves. It is, I'll go here to show you. Yeah, so we require it here, and just in this line, we provide two options. One is the path from which folder to serve the files, and the other is the URL. And for our app, again, the JavaScript and the CSS files are served from there, but also the About page. So we've seen that there is a path traversal vulnerability in ST. So let's try to exploit it. And I will switch here to the terminal. And this one is really easy. So first thing I'll try to do is just fetch the About page. Works as expected. So as an attacker, I will try to escape the folder, right? Like do the ... and hopefully in the end reach the root folder and go for the fastwd, for example. Sorry, what?
Typo.
Oh, I have a typo. etc. Thanks. So if I run that, it actually fails, and the reason is that ST protects against this kind of attempts. It filters out and normalizes the path and prevents the escaping of the folder, out of the folder. But it missed something, and that's where we can encode the docs with URL encoding. So if we just type %2e instead, and again we can kind of repeat this multiple times. Well, I'll just run it like this, and we see that we get into the root folder of the app. We see the package.json file and the source file, so we can actually look at them here. I'll go for the db.js. This is the source code, but of course I can kind of go for the root folder and etc passwd. Again, it's not the most sensitive file on the system. The password hashes are stored in the shadow file, but still, you see that now that an attacker can access any file that the Node process has access to. So this was the first one, an easy one to warn up. And let's look at another vulnerability. And the second one is a package called Marked. Who is familiar with Marked? Okay, many more hands. This is an NPM package used for rendering Markdown, and this is how our to-do app is able to do all this fancy stuff. So Markdown actually supports HTML, and it tries to prevent from injecting script code, right? What we've seen in Mark is the cross-site scripting vulnerability. So the first thing we could try to do is something like that. Right, but Markdown actually protects against this, and it has a security component called sanitize. It's not turned on by default, but in this app we actually turned it on, and it protects us against these kind of things. But what we can try to do is create a link in a Markdown format and do something like that. And again, it didn't work because this was anticipated here by the developers and prevented. And I'm going to cheat a little bit here because I'm going to copy paste the actual vulnerable version of this link. So what we do here is use HTML entities encoding, and this is the value for the semicolon. So as soon as we do that, and also it requires using the closing bracket also to encode it. So you see it gets a little tricky. It's not always obvious how to exploit these things, but when I do that and click on the link, we actually get the alert one. So yeah, this was Markdown. And the last one I want to show you is the Mongo. Yeah, Mongoose library. Who's here familiar with Mongoose? Okay, almost everybody. So our app uses MongoDB to store the to-do items. And it has a pretty basic schema. If you look at the DB file here, we see that the actual content of the to-do item is stored in a buffer. And if you click through the vulnerability details here, we see that this is a remote memory exposure vulnerability, and it has to do with buffer, with how buffer behaves in Node. So I'll switch to the terminal, and let's take a look at the buffer. So buffer can be constructed from strings or arrays, and when we do so from a string, we see that basically a binary buffer is created with the ASCII values of the value we provided in a constructor. So we can say something like this, and it works as expected. It also accepts arrays, and again creates a buffer, binary buffer of these values. But it also accepts an integer as a constructor, and who knows what will happen when I run this. Okay, so a new buffer will be created with the length of 100, but we see that it holds something inside, right? Like we see some data. And if I do it again, we see some different data. So what happens is that for historical and performance reasons, we get a buffer of length 100 that is uninitialized. Basically, what we see here is already used heap memory, previously used heap memory. And if we do it again, we just get to see in more of a heap memory. So, and the reason it happens is that typically when we ask for a buffer, the next thing we do is populate that buffer with some data. So the developers, in this case, said, yeah, we'll just save that time, won't waste the CPU cycle for initializing this buffer. And this is really common in lower level languages like C and C++, but very unexpected in JavaScript. And that's how it led to about 5 or 6, I think, vulnerabilities in different NPM packages, this behavior. And it's a documented behavior, it's not a vulnerability in Node. So going back to our to-do app, if I just somehow can pass an integer to the application instead of a string as my to-do item, I would hopefully be able to see the heap memory of the process. So here I wrote the number 100. Obviously, it was passed as a string to the application. But as an attacker, what I'll try to do is make the application accept this number as an integer. So let's try to do that. I'll again switch to the terminal. And I'm going to use a utility called HTTP. It's called HTTP, but the command is HTTP. And we're going to submit that form from a command line to the application. So what I'll do is do something like content by here, pipe it into HTTP, -- form. As it is a form submission, just going to copy the URL, and the endpoint here is create, and I'm going to ask for the verbose version. So let's try that. So just to refresh the app, we see that a new item indeed was added, and all worked as expected. But I can also submit this data as JSON, as content type JSON, because the application uses the JSON body parser. So I can go here and use the JSON syntax to submit this form. I'll change it to J here. And here I'll just change it to JSON so that the content type of the post request would be application JSON. So let's try that. And refresh. So indeed the item was added, and if we switch back to the terminal, we see that indeed we used, this time we submitted the request as application JSON with this data. So as soon as I use JSON, I can actually now control the type. And if I change this to 800, so we already see that much more data came back, but if I refresh, we see the uninitialized memory of the process. And actually the fun part here is that we see some string of the source code. In this case, it probably was const. But if we do that enough time, and I'm going to ask for only the body, the response body, and base 64 decoded. And let's repeat this for like 100 times, maybe more. And pipe it into some file. So I'll do that, and in the second terminal, I'll just I'm going to see the hex dump of that. So this is like real-time memory coming back from Heroku servers, or from the node process of the Heroku servers. And if I stop here, I could again actually see some source code. So the fix for this vulnerability was actually really simple. It's just, we're looking at Mongoose right now. It just verified that the type, when the type is a number, it just turned it into an array of a single item with that item. And that's it. So what we've seen is the first step. We basically looked at 3 vulnerabilities. We tested our application, and the next step would be to fix them. And let's go here. And if I focus on the project, so let's think we do that with fix PR. We can just click here. We see all the list of the vulnerabilities here, and choose to open a fix PR. Hopefully, will take a few seconds. All right, so we see that all the details, the vulnerabilities that we upgraded the packages from, and also the patches that we applied. So let me show you just the actual changes. So we see a bunch of upgrades. Again, this is a demo app, so many vulnerabilities, but some vulnerabilities we cannot get rid of through an upgrade, because Basically, we pull in dependency A pulls B pulls C. C has a vulnerability, so we are using the latest version of A. We cannot change anything. So we kind of need the developers of B or C to upgrade to the latest version of the vulnerable package. So in this case, what we do is we install, we add a pre-publish hook that runs this command. And it basically looks at the vulnerable packages and applies a patch to them. So we backport those patches and apply them as soon as npm install finishes running. And the last step that we can do is, I'll go back to Sneak here. So the last thing is that we want to watch the projects. Basically, when new vulnerabilities are disclosed, even when we did not change any code in our application, we want to be notified about it. So we do that by watching a project, and we take a snapshot of the dependencies of the project. And when new vulnerability is reported, we just send an alert, an email, a Slack notification, or again, a full fix pull request. And also, we can add the test hook here. So every time a new pull request is created, we are testing the changes, the dependencies for new vulnerabilities. Right. So switching back to the slides. Cool. So these are some JavaScript takeaways. We've seen 3 examples of vulnerabilities, but obviously there are many more. And if you go to sneak.io/vuln, our vulnerability database, you could see this is an opportunity to learn from many other vulnerabilities in open source packages. A few more resources here, our blog, some notable blog posts, and also the Secure Developer podcast that we run. And that's it. I'll be around to answer questions. Please grab me in between the talks if you have any questions or want to talk about security or capture the flag competitions, and also if you want to get a sticker. And thank you.
Thank you, Daniel. Again, we have time just for one question.
So, sorry to take the only question. I wanted to ask, what's your relationship with Node Security Project? Are you using their database? Are you contributing to that? And what's the difference between using NSP check and using SNIC?
Cool. So first, we're good friends with NSP and Adam Baldwin. Our database contains all the vulnerabilities their database has, and along with the vulnerabilities we add those vulnerabilities by our own research. So last month we reported about a dozen of vulnerabilities. We also automatically scan all GitHub projects, all GitHub NPM projects for things that look like a report of a vulnerability or a fix of a vulnerability. So we look at commit messages, we look at issues that are open. So there is this part, and the difference between the two products, I would say, is the fix part. So we basically, both of us kind of detect the issue, but we want to also fix that. So this is not just like this is the list of the vulnerabilities. We created more work for you. This is also our attempt to do the fix, the upgrades, and the patches. So we've seen that briefly, but this is our focus. We want to help fix the issue.